This video describes the data at rest record storage architecture of data as a service. In this video, we're going to try and answer a number of basic questions. What is a record? What do we mean when we talk about data agnostic storage, and why is that important? How do we extend the basic create, read, update, delete or CRUD functionality to CRUD Plus? And how does this work as part of command query optimization so that we separate out the basic CRUD functionality from record retrieval and reporting? We will also be looking at some of the considerations to make this a more sustainable architecture. Finally, the next steps will identify some alternative videos to watch and some other sources of information. Let's start by considering what do we mean by a record. Simply put, a record is a specific instance of a concept. Okay, so two new ideas here, instance and concept. So a concept defines a class of things that we want to store information about. So for an example, a vehicle could be a concept. A concept is going to have one or more data elements. So our example vehicle concept may have a number of different data elements. For example, the make, the model, the year, the seating capacity, and anything else that provides useful information about what a vehicle is. So a concept expresses an idea about something that we want to store in the database. An instance is a very specific single example of a concept. My vehicle has make equals Toyota, model equals RAV4, it would have a license plate, it would have a VIN number, and it would be mine. It is a single example of a concept. So when you think about concepts and instances, traditionally we're going to store records in tables with data elements in columns. How does that relate? In a traditional application, every concept is going to get its own table. And associated with that table, there will be a number of columns which will map to the data elements that we described above. So I would expect that if my database needed to deal with a vehicles concept, that I would have a vehicles table. And within that table, there would be columns for make, model, year, seating capacity, etc. So every concept typically gets its own table with its own set of columns and a set of stored procedures that allow us to select, insert, update, and delete. A traditional relational database design enforces a set of relationships between concepts. So for example, I might have a vehicle, and as child objects of the vehicle, there may be a concept called drivers. And there would then typically be a relationship between the vehicle and the people that drive it. So there would be a foreign key relationship between the drivers and the vehicle that they drive. So the basic definition of a record in data as a service is the same as the basic definition of a record in a traditional database design. We have records that are instances of concepts. A concept is typically a table and an instance is a row in the table. So where does data as a service offer a different approach? Data as a service deals in what we describe as data agnostic record storage. Essentially, instead of having separate tables for each concept within the database, we're going to isolate it into an instances table. This is an alternative approach to a traditional relational database design. If I had a traditional application for, let's say, an insurance policy application, I might expect to see tables for vehicles, claims, drivers, policies, coverages, witnesses, etc. In data agnostic record storage, what we're going to do is we're going to store our records in a data agnostic format, typically either XML or JSON. In the Trellis implementation, we have chosen to use XML as our underlying record storage format. An immediate advantage of using XML is that we have now both traditional simple database field types, for example, strings, dates, numerics, and we can now extend that to complex data types, for example, addresses, contact information, vehicle details, where a single field can contain multiple subfields. And the whole point of XML is that you can store any sort of information within any XML element. This immediately gives us a much richer data storage format. So simply sticking an XML fragment into an instances table is going to allow us to store any information that we want, but it's pretty difficult then to get that data out of the instances table in a useful way. This is why we also encode a bunch of metadata to describe the record information that we've just stored. We want to make sure that we give each individual record its own unique record identifier, and for that we use the instance GUID field. As the name implies, an instance GUID is a global unique identifier. This means that no two records generated by any application stored in the same database should have a collision on the unique record identifier. We also want to know the type of data being stored, so it would be useful if we could run a select statement that would pull out all of the vehicles without having to examine the details of the XML fragments. So we also include a concept GUID. The concept GUID uniquely identifies the concept that the XML fragment is representing. So a vehicle would have a concept GUID that would be different to an insurance policy concept GUID. One of the key relationships in a relational database is typically the parent-child hierarchy of instances within the dataset. So taking our insurance example, the top level record may be an insurance policy. Within that parent, we may have child objects that describe the vehicles on the policy, the coverages of the policy, the claims that have been made. And within the claims, we may have child records that describe any witnesses to the claims or any information relating to the claim. So one of the most common relationships in any data application is a simple parent-child hierarchy, and we represent that in two ways within the application. One, by having a parent GUID, so which instance is the parent of this instance, and we also maintain a hierarchy string which shows from the top of the hierarchy to the current instance how this relates to previous ancestors of the current instance. And we'll look at hierarchy in more detail on a later slide. An immediate advantage of our data agnostic record storage is that it is easy to extend it to include an instance history table. Each instance in the instances table is the current instance of the record. The data version field within the instances table is used to indicate the current version. So starting at 1, if we make a change, we have version 2, version 3, version 4, version 5, etc. And we only need to maintain the latest version of the record in the instances table. As we create new versions of a specific instance, we put a copy of the record in the instance history. So if we are up to version 5 in the instances table, we would typically have instance history records of versions 1, 2, 3, 4, and 5. So we can see when the record was created, when the record was updated, and what the data changes were between each record, because we have a complete history of the record at each version in the XML fragment. So this is a key distinction between data agnostic record storage and the traditional relational database design. In a traditional approach, where I have 100 different concepts requiring 100 different tables, if I needed to create row-level version control, I would need to add an extra 100 tables. So a vehicle table would also have a vehicle history table. A driver table would also have a driver history table. By moving to data agnostic record storage, we can version control all of our records with just 2 tables. The reason we call this out is that it spans across multiple different types of functionality that can be included into the basic create, read, update design. Because we have encapsulated all of the CRUD functionality for our data agnostic record storage into a single table with a dozen fields, we can now extend that functionality to what we describe as CRUD Plus by adding simple extension tables. Another huge difference between data agnostic record storage and the traditional approach to implementing databases is that instead of having to create separate create, read, update, and delete stored procedures for each table, so for example, a traditional vehicles table would have multiple stored procedures for select, update, insert, and delete. Our data agnostic storage only requires a single statement to allow us to insert any type of data into the instances table, and then to read any type of data from the instances table. And this enables us to focus our implementation through a few stored procedures, which we can then extend to provide a much richer set of functionality that will be applied to all instances of all concepts. Let's take our discussion into a different direction for a while. Let's have a look at this idea of record relationships. The diagram on the right shows a simple set of instances A, B, C, D, and E. What we have here is a simple relationship of 5 records, where A is the parent of B and C, C is the parent of D, and D is the parent of E. When you examine most relational databases, the most common relationship you find is a simple parent-child hierarchy, as illustrated by our example on the right. If you think about our metadata from the previous slide, the parent GUID is going to contain the instance GUID of the parent. So for example, in this case, the parent of record E is D. If you remember from our previous slide, we maintain 2 types of information relating to the parent-child relationship. The parent GUID is going to give us the direct parent, and the hierarchy field contains the full path to the record. So, for example, the hierarchy of E is A, then C, then D. The metadata for each instance contains both the parent GUID and hierarchy. This enables us to do fast searches. So for example, I can use the parent GUID to find all of the vehicles that are within a specific insurance policy. Or I can execute a search that would show me all of the vehicles for all of the policies within the database. So if the parent-child hierarchy is stored as part of the instance metadata, where do cross-record dependencies get stored? So whilst it makes sense to store the parent-child hierarchy information within the instance metadata, it is not possible to store relationship between 2 records within the instance metadata. So how does that get represented? So relationships between records are held within the XML fragment of the information. So relationships across the data model are stored within the XML fragment of the record. So for example, in this case, the XML of D may contain an element that references record B. In recent years, security and privacy have become fundamental requirements for most database applications. To maintain privacy of personal information, row-level security has become a prerequisite. We need to be able to identify the people who need to see the data, our users, and we also need to be able to add users to groups to simplify our security process. So for example, I could have a user called Tony who is in the group called Toronto that allows Tony to see customers in Toronto, but not customers in Barrie. In this model, the instance access table is used to grant access to a set of users and groups to specific records. So customer ABC may have an instance record, and access to the instance record for ABC may be granted to a set of users and groups. To be able to see the ABC customer record, a user must be granted access to see the data, either by explicitly adding that user to the instance access set for that customer, or by adding that user to a group that has an instance access record for that instance. Access typically cascades down a hierarchy. So for example, in our insurance policy application, if I have an insurance policy that is visible to the user Tony, any of the child objects within that insurance policy are also visible to the user Tony. However, access to information can be overridden at any point within the hierarchy. So for example, the Tony user may not be able to see financial information associated with the insurance policy, such as credit card details or payments, but would be allowed to see information about vehicles, drivers, claims, etc. So our row-level security model initially defaults to a simple cascade. So as new child records are being added, they inherit the security rights of the parent, and yet we still have the ability for any of those child objects to be able to add additional or remove access from particular users and groups. So this is yet another example of what we describe as CRUD+. So the first example was the ability to add row-level version history using the instance history table. A second example is row-level security using the instance access table. Because we are focusing all access to these tables through a simple set of stored procedures, it's easy to add read audit capability if we require it for privacy. And some applications will also require a break the glass override. So for example, a clinical or hospital application may restrict patient information to certain doctors within a circle of care. However, if there is a medical emergency and other nurses or staff require access to the information, then we can do a break the glass override, which grants access to the additional user, but also flags this as an exception that can then be investigated later. Another key advantage of the CRUD Plus data agnostic storage is the way that we can extend the record storage to include a virtual deletion strategy. So here you can see that the instance access, instances, and instance history tables are mirrored by a set of deleted tables, and we can move records between the active and the deleted tables with two simple requests. So an active record we can move into the deleted by calling a delete request validation, and at any point in the future we can execute restore records to bring them back from the deleted tables into the active tables without losing any information. so we don't lose the history and we don't lose the access rights. And this works across the entire hierarchy of the record being removed. A key advantage of this process is that we can then validate delete requests down a descendant hierarchy. So if you remember the previous slide where we had records A, B, C, D, and E, a user would only be able to delete record A if they were also allowed to delete records B, C, D, and E. And the deletion of A would also apply the deletion to all of the descendant records. So as a block, records A through E would be moved from the active tables to the deleted tables. And at any point in time, the user could reverse the decision and say, oh, I made a mistake, I need to restore A. And as they restore record A, it would also restore records B, C, D, and E. So being able to move records between active and deleted tables with a single command. This is also useful in financial systems because it persists the audit trail even when the user tries to remove the records. So if there's fraudulent activity on an account and the user attempts to remove the evidence, it's only pushed into the deleted tables. And that activity in itself is actually tagged with the user's information. Once we've moved records from the active tables to the deleted instances table, we might want to be able to delete them permanently from the system. So each concept also has a purge cycle. The purge cycle could be purge it that day, or after a number of days, or never purge. So the previous slides identified some great functionality for CRUD+. We have been able to save records, we have been able to track versions of records, we have been able to do some really cool things relating to deletion and recovery of records, but trying to do complex select statements across a single instances table with a ton of XML fields is not optimal. So one thing we have to remember is that we still have the full power of a relational database at our disposal. And although so far we have focused on our basic CRUD functionality through the instances table, we also need to be able to optimize the read operations. And this requires a little bit of interesting data modeling. So from a performance optimization perspective, it makes sense to create some read-only lookup tables using triggers on the instance table itself. This enables us to pre-shred some of the XML data into tables that are only going to be used in select statements to read information, to find which detailed XML fragment I need to consider. In some implementations, we have found it useful to create multiple levels of lookup tables with cascading triggers to optimize search across millions of instance records. Once we have created these lookup tables, it only makes sense to create indexes upon them to further optimize the searches. Again, the CRUD functionality makes it easy for us to create and maintain a reporting database. Essentially what we're going to do here is track any changes to instances and then either pull or push them to a decoupled reporting database. Putting the reporting database on a different server then allows us to run reports without impacting core performance characteristics. These concepts around optimizing record retrieval follow the common CQRS pattern. We have optimized write of information through the database using our CRUD+ functionality and have further optimized retrieval of information using triggers, lookup tables, and indexes. Now let's consider how our data agnostic storage enables us to build sustainable architecture. First of all, we don't need to worry about adding or removing fields. It's just XML. XML can contain anything. Because we only have one instances table, we don't even have to worry about adding or removing whole concepts. So if my insurance policy application now requires a completely new concept to deal with something that wasn't considered in the original design, it's simply a case of adding new instance records to the database with the information that we need to save. Another cool feature of data agnostic storage is that it's easy for us to actually change how concepts interrelate. So we can move concepts up and down the parent-child hierarchy as we wish, as the needs of the business change or as the requirements evolve over time. So another cool feature of data agnostic storage is its ability to be able to reuse existing concepts in multiple places. So for example, I might define a concept of a user action, something a user needs to do by a particular time. I can then add that user action concept as a child for a vehicle, for a policy, for a claim, for anything I want within my application. And unlike a traditional application, I don't need to include a whole bunch of foreign key concepts to other tables. It's all embedded in the hierarchy in the instance. Another interesting feature of the data agnostic record storage architecture is its ability to add new functionality to further extend our CRUD Plus functions. We've covered a couple of examples in our presentation today, adding instance history and instance access, but it can be extended in so many other ways. From a sustainability point of view, our underlying database storage technology will evolve over time. New versions will become available, different vendors will provide different products, and it is easy for us then to change our underlying database storage technology because our core footprint is so small. We have a handful of tables and a few dozen stored procedures that implement the majority of our CRUD Plus functionality within our data agnostic storage model. So as more effective and efficient solutions become available, it is easy for us to migrate our underlying storage technology from one technology to another. The Great Ideas Trellis framework is built on the Microsoft stack, and we're going to use some Microsoft examples to illustrate high availability and scalability. Our data at rest service area is hidden behind a simple external interface. The internal details of how the information is stored is completely invisible to all of the other service areas. This enables us to change the underlying implementation of the data at rest as we need. So for example, for high availability, we might choose a simple clustering solution. Or we could switch to always-on availability groups, or we could deliver the database using Azure SQL as a PaaS solution. And none of the other service areas would know or care. So the implementation of the data at rest solution would not be dependent upon how we actually implement the storage. The data presentation, data in motion, and data in action service areas are only seeing the external interface, are only making calls to save and read records, and so they do not know how we've implemented the internal details of data at rest. So we can also easily scale our data agnostic storage. Obviously, scaling vertically by increasing the size and power of the database servers is an option. But our data agnostic storage also enables us to scale horizontally with no real limit. It is easy for us to partition the database tables. We can do this across multiple file groups and disks within a single database to include the IOPS performance within a particular server. We could also partition the instance table across multiple databases or servers. We can partition using the instance GUID, using the parent GUID, we can partition using the concept GUIDs. There are many different strategies that we can use as part of the external interface to split records between servers, between databases, between file groups. Because the external interface is hiding the implementation, this means that there is no practical limit to the amount of data that we can push into our data at rest service area. Thank you for taking the time to review this video on data at rest record storage architecture. If you are interested in pursuing the subject further, we have created a number of service area videos to support the data as a service architecture. We have also created a number of DevOps videos to show you how Great Ideas implements data as a service solutions. So our greatideas.com website provides a lot more information about data as a service. We provide extensive documentation on the data as a service architecture, and we also describe the implementation of Trellis, the first complete data as a service implementation. We hope you have enjoyed this video and found the information presented useful. If you want to know more about data as a service or the Trellis implementation, please reach out to us at the website. Thank you very much.